Yeah, thank you for coming. I hope the talks were interesting. This is the end of the first day. We are going to talk about agentic RAG and what's new in OpenSearch on this topic. You already saw a talk like 1 hour ago, which was kind of an introduction, so we will go further and give you some demos and some show you the innovations that are happening in OpenSearch. So we are, I'm Lucian, and I'm here with my colleague Pietro. We are from Adelean, and we are a search company. We do consulting, training, we integrate OpenSearch, Solr, Elasticsearch. We also develop two software. One is a e-commerce search solution, and the other one is an enterprise search solution that's similar to the, like, let's say, the GitHub of search engines. Yeah, so you've seen throughout this conference the previous talks and all that, how search evolved. We moved from keyword-based search to something that's more conversational today. So the journey was long. Like this is a screenshot from what's considered to be the very first search engine on the internet in 1997, something like that. So we've been through semantic search, hybrid search, question answering, RAG, retrieval augmented generation, and now with agentic RAG. So one big step forward was the arrival of LLMs, which some thought of like the new search engine, but actually it was not a replacement, it was an add-on. LLMs like give answers also like the search engines, but we realized that the answers the LLMs give are not necessarily accurate, so we moved to retrieval augmented generation, where we put together search engines and LLMs. Okay, so yeah, no real-time knowledge for LLMs, no specific domain knowledge, no source citation, and sometimes like hallucinations with wrong data sources and stuff like that. So again, we ended up with retrieval augmented generation, which is combining the search engine with the large language model. So the search engine gets the question answering, the summarization features of the LLM, and the LLM is better on hallucinations and on source citing and on the answers that it gives.
But, oh, that's so strong. RAG sometimes we saw is not enough. It's really good because we can ground our knowledge to the LLM, but sometimes it's really not enough. Let's take, for example, this query. In this query, we are looking for the top 3 business models used by AI startups in 2024. And we are asking specific question about it. Why a standard RAG is not enough? Because it's limited to one-step retrieval, so it's extremely static. We may have some problem because sometimes we don't retrieve the correct information, and in that case, well, the large language model won't be able to answer us. Sometimes we retrieve not enough information, so the K retrieved document is not big enough. Also, it's not capable of reasoning like a human can do. It's not able to loop, to iterate, to check one fact, refine the query, retrieve again. For example, in this case, it may not have found the 3 top business, or it may not have found the answer to the second point. So it's limited. It's limited to static retrieval. And prompting technique like chain of thought, well, they can't solve this problem. And that's why we took the best from LLM, we took the best from search. So we said, well, let's take the best from agent as well. What are agents? Agents are autonomous systems that perceive the environment, make decisions, and take action to achieve a goal. I want really to focus here on the fact that it works iteratively. So we saw the problem of the LLM. If the LLM is not capable of reasoning, well, the agentic RAG won't be able of reasoning, but we're going to do some sort of a simulation of reasoning through this iterative refining. And so in the case of agentic RAG, the LLM has to act as an agent. This means that the LLM has to take decision. Well, yeah, it has to choose for the next action to take or to the next query. It must be able to use tools, like must be able to search, it must be able to create code and call APIs as well. Once again, I want to go back to the fact that there is some sort of reasoning loop. So the LLM and the agentic RAG needs to get the answer and to refine it and to evaluate progress and adjust each time at each iteration. And finally, of course, to do all of this, the LLM needs, of course, a memory. So these are really the four things that the LLM, the four verbs that the agentic RAG has to respect. So perceive, plan, act, and reflect and adjust. We already saw some example of agentic RAG. Well, on your left, you can see agentic RAG without agentic behavior. Over LLM without agentic behavior, we ask the LLM what is the weather today, and it can't answer us because it doesn't have the data. With agentic behavior, the LLM is going to be able to call a tool to retrieve the information about the weather, and is going to be able to give us an answer. So how did we get our first agentic RAG? So one of the first approach, as I said before, was trying with prompting techniques. So we had chain of thought, self-consistency, and tree of thought. So the goal here was really to make the LLM reason like a human, so step by step. With different technique, of course. We had parallel reasoning in the case, for example, of tree of thought. But once again, this approach was, of course, limited, but it was already the beginning. Then there was the introduction of React. So React was introduced in 2023 in a paper synergizing reasoning and acting in language models. So React means reason and act. And as you can see in this example, it works fairly well. The idea here is that the large language model is going to be able to reason and to act. To reason means that the LLM is going to somehow think, so it's going to think step by step, like we have in chain of thought with chain of thought prompting. But then it has also the capacity of acting, and acting means, for example, to call functions. Like in this case, the LLM is going to be able somehow to call a function. For example, it's a search function, and it's going to look for a remote, and then it's going to iterate. And as you can see, there are many steps, and you also have the observation. So each time that the LLM is using a tool, it's actually getting the answer and trying to observe somehow the answer. Now, React is a prompting technique, so everything is based on prompting. Here you can see one of the prompting example. Once again, we need a memory, and we are iterating. At each iteration, we try to get closer to the answer. And we can also invoke tools, of course. Now, the problem here are many. So since everything is made through prompting, results may be inaccurate and, of course, subject to changes. As the LLM need a memory and has to iterate to get to the closer answer, but the problem is that the memory is limited to the LLM context windows. And finally, the process of calling and invoking the tool, it's a bit messy because each time there is some sort of parser that have to retrieve the argument to use for each function, and then so the LLM is interrupted, and then everything is copied back to the prompt and sent back to the LLM. So it's really a messy approach. But once again, this approach brought us to what we have today. So today we are used mostly, but not only. We still use React, but the community is using a lot of tool calling. It's more structured than React. The idea here is really the LLM is acting as an agent, as you can see. So, of course, if the LLM has the answer, it's going to answer. If it doesn't have the answer, it's going to call a tool, it's going to use this tool to interact with the environment, and it's going to give the answer. If it doesn't have the answer using the tool, it's going to try again, probably. And tools are generally defined by name, descriptions, and parameters. As you can see in this case, we have a function for flights, for searching for flights. So we have different parameters. We have a departure city, arrival city, a travel city. And this is an example with the OpenAI. If, for example, we ask what flights are available from Paris to San Francisco on December 7th, we give the tools as parameter to the client, OpenAI client, and the LLM is not answering us directly, it's actually calling a function to get, of course, hopefully the flight that's going to bring us to San Francisco, using, of course, all the arguments that we find in our function. Now, in the last months, last years, there has been a huge problem. Actually, every LLM provider was actually implementing its own way to implement tools. So we had for each LLM a different tool, and for each service, like we see here, OpenSearch, GitHub, and Slack, and Chrome, we had a different implementation. So there was really a fragmentation of the implementation, and it was really too hard to scale it, to integrate. We're really having too much work for nothing, until the day that in November, Anthropic introduced a protocol that tried to standardize how apps provided the context to large language model, just like a USB Type-C that helped us to connect and charge our computer to every port. We were having something that was absolutely standardized, that we could connect to any LLM, so any LLM like Claude, OpenAI LLM, and that was giving, let's say, some more free time to developer, that they didn't have to develop the same thing again and again, but they could just use the same standardized approach. And as you can see, you have the link to the GitHub page. You can find the presentation on the OpenSearch schedule. There are many adopters here. There are just a few of them. Of course, we have OpenSearch with them. But there are really thousands of adopters of this protocol.
Yeah, so moving on to OpenSearch, because this is why we are here. So the journey of OpenSearch since the very first release, and even since before that, but if we focus on the AI journey of OpenSearch, we've seen that things move very fast lately. So this year we are talking about agentic RAG. Last year we were talking about RAG. The year before we were talking about semantic search and vector search and vectorization. And the year before we were just like talking about like keyword search. Okay, so there has been many evolutions into OpenSearch, and it's accelerating, yeah. So I don't even know what we will talk about the next year, but it's getting very powerful already.
Here, I like to focus on a few things, like, as you can see, connectors, conversational search, agent and tools, and MCP server. We're going to see all of this in the next slides. So here I have some sort of definition I try to bring about what is an agent in OpenSearch. So an agent, we have to see it as some sort of coordinator that use a large language model to solve a problem, and also an agent use tools in order to solve a problem. We have 4 types of agent in OpenSearch. So the first 2 types, the flow agent and conversational flow agent, are essentially agents that to which we give a workflow or tools, and this workflow is fixed. So the first tool will give an output to the second one, and the second one will give an output to the third one. And the only difference between the flow agent and conversational flow agent that the second one has a memory, so it's really useful in chatbot. The conversational agent instead is able of reasoning, so, well, kind of, is able, has the possibility to choose between tools. So it doesn't have to stick to a workflow. It can pick the tool it thinks is correct and try to get an answer to our query. The plan and execute reflect agent uses the conversational agent, but has the capacity also of doing a plan, so multi-planning, and using different conversational agents to solve each step of this plan. So as I said, each agent uses somehow tools. Some are stick to a workflow, some they can pick the one they want. And in OpenSearch, we have 3 types of tools. So we have some standard tools that were introduced with version 2.13, that they were introduced before the introduction of Model Context Protocol, and are compatible with all the type of agent. Then we have MCP tools in 2 different flavors. So we have internal server and external server. So for instance, both were introduced around version 3, but MCP external server is usable from version 2.09 because we can plug it in with using connectors. Both MCP internal server and external server, of course, can use only the 2 agent that they don't use the plan execute reflect agent and the conversational agent, so not the flow agents at the moment, of course. So as I said, we can use, there's a list of standard tool. We have, we can see, this is the version, the last version. So we have tools that can essentially do a cat indices. They can get the different indices in our cluster. We have tools that they can call a machine learning model. Some other tool that they just do a search or a semantic search. So for example, if we take a flow agent, we can implement our retrieval augmented generation system using 2 different tools. So once again, flow agent, we have a fixed workflow. We take the vector DB tool that does vector search, and the ML model tool that call a large language model, in this case, because we want to implement a RAG, and the large language model will get the result from the first tool and give us an answer. This is quite already enough for many use cases, but there is also the possibility of implementing the tool interface and adding new tools. Then, from version 3, there is the possibility to use also MCP. In this case, we're talking about MCP internally deployed in OpenSearch, so internal server. We need to activate MCP in this case, and tools have to be registered before use. So there is no tool registered. We can get the definition of the different tools from the OpenSearch documentation. Once we have registered them, we can use them. In this case, there's the possibility also to list all the available tools. And then there is also the external server, as I said, that we can connect through connectors. And in this case, it comes with standard tools. Here you can see some of them. So there's the cat indices tool, the index mapping tool to get the mapping of an index. And so this one are already activated, so we can already use them. But then there is the possibility to extend tools by registering them in the MCP server that we're gonna see in the demo later, like in a few minutes. So in this demo, it's quite simple. We are connecting our model through connector. We are going to use a plan execute reflect agent, and we're going to use basic OpenSearch tool and first time. And then we're going to extend using MCP server, and the use case is going to be e-commerce. How much time do we have? I don't know.
We have like 10 minutes.
10 minutes?
Before the search party.
13, no? Okay. Gonna try to zoom it because I think it's gonna be too big, maybe, no?
Maybe you can clip the mic on the lanyard.
Yeah, I was gonna work. So, sorry for the spoiler. So I'm on version 3.1. In this use case, once again, is an e-commerce use case. Well, since I'm Italian, I like to talk about food. It's not just a stereotype. So the idea here is to try to simulate some sort of a smart chatbot somehow that can essentially retrieve information from our cluster. It doesn't know anything about the cluster, but it can use tool to retrieve information from it. And then I'm gonna ask him a question, and it's gonna try to answer us. So I started this with the indexation of a few receipts. So we have a receipt index where you can see the name of the product we want to make, the different ingredients we need, and the instructions. We have some products that are quite famous, like pizza, and there are some products that are really unknown to large language model. This is something from where I come from, that I try to ask information to ChatGPT, and he didn't know. So I was sure that I could use and make this demo net. And then I have another index that contains different products. So we have to see this as a list of products in a supermarket. So we have the name of the product, the brand, and the price. As you can see, there are many ingredients. Some are useful to make some of these products. For example, this focaccia, that is some sort of salty bread in Italy. Most of the time, not always. And as you can see, we have also the price. So one of the first things we need to do in this case is, because we are in a demo, we need to activate to set cluster setting to use also on data node, which I already did. Then we need to register a model group that we can use to then register our model. Each time we do this, we're gonna retrieve an ID. So in this case, I'm not gonna register my model group because I already have one that's called like this. But each time I do this, I'm gonna have an ID. So I'm gonna need to use this ID to do the next step essentially. Then I'll create a connector. So a connector in this case is useful to connect to a large language model. In this case, I choose OpenAI. everything here, you can find it in the documentation, so it's really straightforward, and we are just actually connecting to the endpoint given by OpenAI using the credential that we hide in this case. And we're going to send a request body where we send the parameter model and the messages. Even in this case, we're going to retrieve the connector ID, and we're going to use the connector ID of the model, the connector ID and the group ID to register our model, as you can see here. So the connector ID and the model group ID. In this case, we finally have the model ID that's going to represent our model, essentially. So to give a try to this, and I hope it's going to work, because as usual, when we do demo, it never works. In this case, just a test to test that our model is working. We ask, we say anything. I mean, we give a system prompt, so you say to make jokes in case. And we see that the model is already answering weirdly, like trying to make jokes, maybe not. Once we have done this, once we have tested that the large language model is actually connected, we can register our agent. To register our agent, well, we need to follow the doc, and we need to specify what type of agent we want. So in this case, I'm using a plan, execute, and reflect agent. We're going to use, once again, the model ID. So the model ID is the same that we used to call here to send the message. We're going to give a type of memory. So in this case, it's stocking everything in an index. So it's a conversion index memory type. And then we have the list of tools. So in this case, I specified a list of tools that the agent is going to be able to use. We have the cat indices, we have the tool to get the mapping of the index, and then we have the search index tool. So with these three tools, despite the large language model doesn't know anything about the cluster, is going to probably be able to retrieve the indices, try to understand which indices are the one that should be queried, and then it's going to create its own query and get the result and try to reason somehow and give us the answer. So once we have done all of this, I ask to the agent what ingredients and what cost to make the focaccia, so the one that I specified in the first index, and give me all products I need. If I do this, I got something that is similar to this. So we have all the different steps from which our agents went through. And at the end, we have our answer with the different ingredients. And this is, everything is the same as we can find in the index. So as we can see, for making the focaccia, we need all-purpose flour, and we have. And we also have the Italian flour, 1 kilo, that costs exactly $2.50. We also have in the ingredients the Manitoba flour that we can find somewhere here in the index, yes, that costs $3. There are some information that the model was not able to get, because here we're taking some product of the lemon, but overall it's quite surprising how the large language model could use the different tools we gave him and could give us an answer.
It's not the answer.
Is it not the answer?
No.
Why?
Because you don't put a kilo of sugar to make focaccia with 2 kilos of flour. Something's wrong there. It's not scaling things properly.
Where is the sugar? Yeah, but I asked her to give me all the products I need. I didn't ask the receipt.
You asked for the cost to make it, not the cost of the individual ingredients. So it's completely wrong.
No, what ingredients and what cost to make it. Yeah. So he gave us the ingredients and the cost to make it. Well, they didn't give it the full cost, but well, we can calculate it. Then in this case, this is simple demo. So in this case, you can specify a system prompt, and we had the occasion to look at really complex system prompt used by OpenAI. In this case, I didn't put anything, and it's already surprising, I think, the answer that the LLM gave us.
You will have some leftovers, but if you ask, if you plug this with a supermarket, so they will give you the list of the products that you should.
You asked for the cost of the focaccia, not the cost of the retail packages.
So I didn't get that. Okay. We can talk about it later, because to me, I think it's normal behavior in this, but okay.
Demos show the best case.
Yeah. I hope we still have time, because I want to show you one last thing. So the second thing I wanted to show you is actually how to connect your external MCP server to OpenSearch and be able to use tools that I specifically created and implemented in the MCP server. Once again, this is common connector knowledge. So one of the things we need to do is to add the regex for trusted connector. In this case, I'm into a Docker Compose, and I have my OpenSearch MCP on the port 9900. As before, we need to use connectors. So this is why we can connect our MCP server from version 2.09. Once again, we'll get our connector ID, and then we register our agent. In this case, I'm using a simple conversational agent. And in this case, I'm giving the MCP connector and the web search tool. So for the web search tool, is not between the standard tool offered by the MCP server. So I decided to, I don't know if I can zoom this. I have no idea how to do it.
Yeah, I think it's...
Okay, but I'm going to just go super fast on this. So it's quite easy and to implement, and everything is in the doc, and you can have a look at it, and it's really easy to implement. So in this case, I'm just implementing a function that is calling Google API, and it's gonna retrieve all the results about my query. And I'm gonna register this function through this tool. And also, I'm gonna specify parameters that the LLM is gonna call in the tool parameters. In this case, it's just this simplest thing was to have just a query. And one nice feature of all this is that we can use tool filters. Tool filters is usable for picking the tools essentially that we want to be used, and because the MCP server exposes different tools, maybe we have implemented 100 of them, and so we can use the tool filters to just get the one we want. And in this case, the demo is as some sister prompt, and I'm just gonna ask to the large language model what is this focaccia, and it's gonna I'm gonna try to do it live, and it's gonna normally work. Yeah, it's gonna get the information. Yeah, it gave us too many information probably. But I can tell you that it's from a Puglia region, that it's for sure. And these are all information that the large language model was able to retrieve through the internet. Because you have to trust me on this. It doesn't know about. You can try it at home. It doesn't know about the specific product. So this was, the demo.
Okay, so in conclusion, very quick conclusion. So you have seen that search engines evolve rapidly. We are now at the point where OpenSearch can, call APIs and construct an answer. You have seen that RAG works and does things, but agentic RAGs like corrects and adds like this iterative reasoning, let's say, to this. And the important part that you have to be aware of is that you have to configure each part so it works properly in total. Yes. And you can find kind of all of what you saw here in this blog post if you need to get into it later. And yes, that's it. Thank you. And